Couple of quick things before we dive back in. So seniors, I put in the drops and the double test score, I think, yesterday. If you don't want to do a double and you'd rather do a retake, send me an email, let me know. Otherwise, aside from this weekend's homework, that'll be all there is for the semester. So kind of where you'll be, after Sunday's problem set, that's the last thing that you guys need to turn in. That'll be it for you guys. So if you don't like where you're at and you want to do something different, or you need to get some stuff in, kind of get that taken care of and should be good. Next week we'll talk about if you need to take the exam, what the DLO is for that stuff too.
Do you not have to take
there's an attendance component also.
Dang it. That's right. It's like excused absences.
So that's for seniors. I don't know I just get an email saying these are the people in your classes that have to take exams because of their attendance.
We have to take exams no matter what for juniors.
Yeah.
Has to be 5 and next year.
Second semester, no.
Yeah.
In AP classes, we only take the AP test for just do like a
My AP seniors don't have a project in lieu of an exam. They just have the AP exam, which is AP Calc exam is hard enough. They just worry about that. All right. So last time we had left off we'd been talking about exponential functions, and we were like in the middle of this example problem when I ran out of time. So I want to pick up here where we left off and finish up this example. So I've just kind of copied and pasted in everything that we had done from last time. So just to rehash here, the problem said given the population of a certain city in 1990 is 782,248 people, and the population of the same city in 2000 was 895,193 peoples. And assuming the population growth is exponential, in what year will the population reach 1 million? We had pointed out that this was really kind of a two-step problem. In step one, we're going to have to write a model. And in step two, we're going to have to solve that model where it's equal to 1 million. So we've started in step one. Since this was the population growth is exponential, we knew we were going to write an exponential equation. So we could either write a times b to the x or a times e to the kx. We selected the first one. It doesn't really matter which one you do. I think for our purposes, this is going to be the easier one to make the model with, though. I then said, okay, well, I can think about the year and the population as a point. Since I'm given 2 dates and 2 populations, that's like having 2 points. So I just kind of rewrote that information to a table. And I looked at that and I went, this would be a lot nicer if one of these x coordinates was a 0. That makes writing the equation a lot easier if one of the x coordinates is a 0. So I pulled out this neat little trick and I just said, okay, what if I trade out this variable x for the variable t, where t is just the years after 1990. In that case, 1990 would turn into 0, because it's 0 years after 1990. And 2000 would turn into 10, because it's 10 years after 1990. So what I'm going to do is I'm going to write an equation for this information, because it just makes the writing the equation part way easier. So I went and plugged in the first point into my model. When I have b to the 0, that's simplified down to 1. So I just get that a is 782,248. I plugged that value in, and then the second point for f of t and t, and then I solved. So I divided both sides by 782, 248, and then took the 10th root of both sides. So just to show you on your calculator, to take a 10th root, you can type the number 10, press the math button and select option number 5, and that'll make a 10th root. And then we just did that to 895, 193 divided by 782, 248. So that's how I got that 101 number. So what I have now, I can say, is that f of t is the equation 782,248 times 1.0135780 to the t. That's the end of step 1. Step 2, then, what I need to do is solve my equation f of t equal to 1 million. So I'm solving that for t. Everybody okay there? Okay. So to solve this for t, what am I going to have to do? All right, that's an equation that I want to solve for t. What would I do to do that? Anybody got any ideas? Okay, so what operation would I need to do to both sides to get rid of that 782? Yeah, so I divide both sides by that, so we could do that. And I'm just going to write it as this for right now, until I get the calculator back out to actually do the number. Everybody's okay with that? Now, how am I going to get the t out of the exponent there? Well, I mean, you can do that, but then you just have like the t over here then, right? So it's not getting it by itself, right? So that doesn't, you can do that, it just doesn't really help us. You know what I'm saying? Anybody else got an idea? Well, this is good. This is what should have happened. You know why? We don't have the algebraic tool that we need to do this yet. We can still do this problem, but we can't do it algebraically, right? Later on in this chapter, we will learn the algebraic tool we need to go back to do this, but we don't have it yet. Ideally, if this was truly review, you would remember the tool that you needed to use here. But since we're seeing this for the first time, I understand that you don't, and that's okay. So what can we do? If we can't do this algebraically, but Mr. Kulik claims we can still do this. Yeah, we're going to use our calculator to do this. And how are we going to do this on our calculator? In general, anytime you have a problem you cannot solve or don't know how to solve, the calculator can do this for you. You just have to know how to ask. So think about what's really happening here. We have, I have some like exponential function. This is like my f of t. And then I have like a population, say like here. That's 1 million. Yeah, so what we're going to be doing on our calculator then is finding the intersection to figure out the value of t that we need. Anytime you run into an equation that you're not sure how to solve, you can do this same technique on our calculator. Like if you're taking an ACT or SAT or some kind of standardized test, and you run into something like, not sure what to do with that, you can just do what we're doing here, and you can just type in the equation to both sides and solve it. Mr. Kulik's going to be a little fancy. He's going to store that entire number into the letter B. So what I did is I pressed the STO button. That's what gives me the little arrow. And what that's going to do is it's going to save that number, that 1.01, and all of its decimal points into the letter B. So I can use that when I write my equation over here. That way I can be as like accurate as possible. Now, if you just took like 4 or 5 decimal places, it's probably going to be fine. But I'm going to, I'm going to store all the decimal places into B and use them all, since I'm fancy like that. And it gives me an opportunity to show you how to do this thing on your calculator, which is a nice thing to know how to do, right? Okay. I'm now going to set up a window in order to view this, because probably on the standard window, I'm not going to see diddly poop on this. So let's think about this. It took 10 years to go from 780,000 to 890,000. So I'll go from 0 to, say, I don't know, like 25 or something. There's probably enough time to get up over 1 million. You guys buy that? Okay. And then the Y's are my population. So my population starts at 782. So I'll do like my Y minimum, I'll make 750. And I have to get north of 1 million. So maybe I'll do like 1.25 mil. That seems appropriate. And I'll just change my scale to go up by 100,000s. And then let's hit graph, and I should get a pretty decent picture. There's my population curve. That's my f of t function. Here's my 1 million line coming through. I see a nice intersection there. How do I find the intersection on my calculator? Second trace, and then I'll just pick the intersect command. Enter, enter, enter. And I get 18.21 years. Is that really the answer, though?
No.
Because what is the question actually asking for here?
So we got to do 18.2 years after 1990.
Perfect. Yeah, it asks for in what year. Remember, T is the years after 1990. So this is between 2008 and 2009. So somewhere in that 2008 calendar year, early on in it, in the spring probably.
Around February.
You think February-ish?
That's what I'm thinking.
Okay. Well, let's get fancy here. So I'll do 18.209 times 365.2. Oops, I meant just point. Oh my goodness. Just 0.209. So 76 days into, so we're past February.
Sadly,
Yeah. So what, there's 31 in January, 28.2 in February. So around March 17, 18.
congrats.
Thank you.
Good guess. It's a 1 in 12. weighted much closely to like those first 3 or 4 months. If you guessed December, I would have been scratching my head and gone, Yeah. It's probably 50-50 between March and February at that point. All right. So again, this graphing trick is going to be how we'll solve these exponential equations until we talk about, I don't know, be another section or two before we get the tool we need to do this algebraically. But remember this trick. It's an excellent standardized test trick for those of you that still have ACTs that you're planning on taking again. Probably most of us taken it once already. But that'll, you can pick up an easy 5 more points or something in your math section just by using that trick to solve stuff you're like, I don't know how to solve that. Doesn't matter. If you know how to set it up in your calculator, just let the calculator handle it. Right? All right. Now, so what if I asked you what the population for this problem, or in this situation, what would the population be, say, in the year 21, 2,100? So what are we doing? We're plugging in 110 in for x, right?
Yeah.
So let's do that. So press vars, yvars, function, y1, and we'll do 110. So the population of the city is now like 3 million. That seems a little fishy to me.
Yeah.
Right? Like, a city that's gone from 700,000 to 3 million people inside of a century.
Fishy, but it could be like New York.
Yeah, starting in 1990, you expecting another city to do that? Like that's awful. That's awful fishy there. And like, what is that going to require logistically for a city?
Lots.
Like a lot of vertical growth, right? Like you're building upward rather than out because you have only so much out you can do.
Gotta go up.
So one of the things about this exponential model that we're talking about is that under ideal conditions,
It's good.
it's a good model for population, right? But most population is not,
Constantly growing.
under ideal conditions like that. I mean, it's at one point you'd expect like maybe it takes a little while for things to get going. We grow a whole lot, and then the growth rate slows down and kind of stops once you get to like the carrying capacity where you run out of resources, right? You guys kind of get the idea? So that's what we want to look at. So there is another model that we can use that will describe that situation much better. It's called logistic. So this is like the logistic growth function. So we have f of x equals c over 1 plus a times b to the x. Or you could write it as f of x equals c over 1 plus a e to the negative kx. And we have some constraints here. Since this is growth, these guys have to be positive and b has to be bigger than 1. So we have some vocab here. We call C the limit to growth. Or sometimes it's called like the carrying capacity. So that would be like the upper bound of what population is possible before resources are completely depleted and there's really just no more growth that can happen. You're out of land or water or food or whatever. So if the B is between 0 and 1, or the K is negative, then this would turn into a logistic decay situation. So I have a question here for you. If we look at the limits, and I'll just use this first one. Let's think about what these limits should be. Okay? So in this first limit, A is going to negative infinity, right? So if I take a constant, B, and I raise it to a very small number, like negative 10 million, what's that going to do to B? It's going to make it super small. Well, be careful with what do you mean by super small? We should be careful here. Because it'll make it smaller, but it'll only make it so small. So let's think about this. We have 2. Let's say 2 is our B. If I do 2 to the negative 1, that is, it's not negative 2. It's 1/2, right? It makes the reciprocal. If I do 2 to the negative 2, it becomes 1/4. It's 1 over 2 squared. If I do 2 to the negative 3rd, it's 1 over 8, 1 over 2 to the 3rd. So each of those are getting smaller and smaller and smaller, but they're approaching a specific value, which would be 0, right? Eventually, if that gets infinitely small of a number in the exponent, that eventually goes to 0, right? So if we're plugging negative infinity in for B, and that becomes 0, A times 0 is 0, and 1 plus 0 is, and C over 1 is C. So we expect that to be an asymptote, or the end behavior on the left side. And if we do the same thing here and we're plugging in positive infinities, what's going to happen there? Yeah, so B is going to get really infinitely big, right? So something big times A, still something big, right? 1 plus something big, still something big. if I have a constant divided by something enormous, what are we heading towards? Well, like think about 5 over 10,000 going towards 0 again, right?
Yeah.
Huh. Let me look at this for just 1 second. Well, let's just look here. So let's look at an example here. I'm trying to figure out if this is a typo because it feels like it's a typo, but let's do the graph and check it out ourselves. So let's graph this logistic function. Now, if I'm going to graph this, I definitely want to use the fraction command on my calculator. And I'm going to go ahead and set my window. So maybe I'll go just from -10 to 10 on the x's. But the y's, I know I should be going between 0 and c. So 0 to 10 seems good to me since c is 10. So let's take a look here. Okay. So here's we made a little bit of a goofer here. I see where it is. Oh no, we didn't. What we did was fine. This is not yeah, okay. So there's a typo in my notes. Felt like there was. Oops. That should be -x.
That's a game changer.
Yeah. So if you do that, that's a 0, and that's a c. My apologies. So if I look at this guy, and let's just, this thing I just graphed here. I'm going to turn the axis off. At the bottom of the screen, that's y equals 0. The top of the screen is y equals 10. Those look like our asymptotes, right? Y equals 10, y equals 0, which matches exactly what we would see here. Everybody's okay? What if we had this one? Okay, hold on 1 second. I think I want to change what I edited. I don't think I want to make that -x because everything else is going to be informed. I see what the typo is. That was fine, but it's going to screw everything else up to the extent I don't want it screwed up. This is what I want to do. I just want to change those.
So b is just b to the regular x.
Yes. Yeah, I just want those to be b to the x's, but I want to change the growth situation to be less than 1. And the reason is if I take a number less than 1, and I raise it to a negative power, it's going to be getting bigger, right? If I take 1/2 and I do that to the -1, it becomes 2.
Yeah.
So that's going to do what I need it to do now. Okay. All right. So that's what I wanted to have. Okay. So let's take a look here. What would I expect my horizontal or asymptotes to be for this g of x? Always 0, and the other should be the c, which is 31. Let's just kind of confirm that in our calculator. Oops. And again, I'm going to change my window here. So I'm going to stick at y0, but I'm going to change the y max to something that's bigger than or equal to 31. Maybe I'll do 32. And again, I have my axes off, but you see, again, y equals 0 and y equals 31 look like our two asymptotes. Got this nice, pretty S-looking curve here. Is it time to go? Okay. We'll see you guys after lunch. Left off talking about these logistic functions. We've talked about how to find like their asymptotes. They have 2 of them. What if I wanted to say like find f of 0? What would I have to do there?
You plug in 0 for that x, right?
Yeah. So what's that going to become? 10 over 1 plus 3, or 10 over 4, which just turns into like 6 over 4. 6 over 4. Come on, Mr. Kulik. Where did the 6 come from? 10 over 4.
It was the
5 over 2, right? But what would this represent in the terms of like a population? It's the population at time 0, or the initial population, right? Yeah, that's your starting population, right? So if I wanted like f of 10, we'd plug 10 in for t, or x, or whatever, and that would then be the population at time t equals 10, right? Okay. So I just wanted to be clear as to like kind of how we could use those. Let's look at one more example, and I think we can be done.
Will you give us a homework?
Yes, sir.
Sweet.
All right. The population of a city can be modeled by the logistic growth equation, yada, 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 where P is the population of the city T years after 1950. At the beginning of what year will the city have 1 million people?
That's a problem.
Okay. We're looking for the year, so we want a value for T, right? When will the city have have 1 million people? That's a population. So what I want to do is I want to solve that P of t equal to 1 million. Everybody okay with the reasoning there? Guess how we're going to do this?
Same way we did the last one.
Yeah, the same way we did last one. We're going to graph it on our calculator and look for an intersection. All right, I'm going to turn off these other two because I got to do this all again in like 15 minutes. So I'm going to leave those in there. So just type this into our old friend, the calculator.
Whoever invented the calculator is smart.
Well,
Because it's very.
yeah, it's quite helpful, right? The man commonly credited with the invention of the computer is Alan Turing.
Oh, I know.
Yeah, the imitation game. Yeah, that's probably. Had Benedict Cumberbatch in it. That's the imitation game. So got it all set up. I'm gonna have to reset our window though.
Yeah.
So it's a population thing. I don't know how long this is gonna take. Maybe let's go like 100 years or something. I'm gonna give it a lot of time. Since that's pretty near the carrying capacity, right? The carrying capacity is like 1.4 million. So I'll do 0 to like 1.5 million maybe. And go by like 100,000s. So here's our population function. There's our 1 million. And I just need to find that intersection. Second trace, intersect command, enter, enter, enter. 79.00 whatever. Okay, does that actually answer the question though?
No, just gets us a step closer.
Yeah, it says at the beginning of what year will the city have 1 million people? So I should just do
Make it in
1950 plus 79.
79. Yeah, so like,
Okay.
2029.
Yeah, 2029. Is that the right answer? Everybody agree with this?
Actually,
Let's check. If we do y1 of 79. Oops, that's not what I meant though. We put it in y3.
yeah, Y3.
Oh no! You're really counting on that, weren't you? The disappointment is palpable. So really, what year should we use? At the beginning of 2029, we're just shy of 1 million.
Yep.
So this is because it says at the beginning of the year. So we have to round up to the next whole number, no matter how small the decimal we have. Pretty rude, dude.
Sucks.
But that's the actual answer.
That's how we do it. But
So at this point, you guys should be able to do through 16 on the problem set.
Mr. Kulik, I have a serious question.
All right, I have serious answers.
Let's go. Do you like Dasani or Smart Water?
Smart water.
Dasani.
No, dude.
Dasani is the worst.
Guys, who likes
Dasani's
Dasani?
actually the worst.
I don't know that I have an opinion on bottled water brands.
Really? No, this is like a big thing.
Well, like, okay, there's
But if we're talking about
like water, and it's like carbonated. and Dasani.
Yeah, there's that carbonated.
Oh, you're talking about like sparkling water?
It's like
It's
not salty
not.
water, but it's like it has a little bit of carbonate in it, but it's just because it's got like
I like chocolate.
Carbonate or carbonation?
carbonate water.
It's so salty.
You can't take salt in that.
Yeah, that's even worse.
No, it's literally.
You can't even
There's
taste
not
it.
a big difference between that or.
Oh.
It's because you don't like
Give
water.
me
Give me your water.
Kirkland?
That water.
Oh, it's tough, dude.
Yeah, you throw your smart water. I handed her mine aside. That. She can't handle a bottle anyways.
All right, here's gonna be my answer. You ready?
I'm ready.
Which one? Everyone's cheaper.
Dasani. Dasani.
No, Kirkland purified water is
Dasani
cheaper.
is cheaper.
That's how you gotta go.
Water is water is water.
Yeah.
Now take it off. That's ocean water.
Oh shit.
You can't taste it.
Yeah.
It doesn't have carbonate, but mine's 100% recyclable.
Mine is
Mineral
mineral.
now.
It doesn't have
Potassium
ABCs.
chloride.
No, but
Mine's salt. I'm done with it. It has salt in it.
Yeah.
How do you feel 100% recyclable?
Yeah.
Where's
Jaden better rock Coachella here.
Alright, Dasani, thank you.
Like regular, like the purest of pure, like well waters have salts and minerals and stuff in them.
This has minerals for taste.
Yeah. Yes,
Electrolytes.
Sure.
Even better.
All right.